Now we switch from images to language. And the very first problem is that a neural network only eats numbers. So how do we turn a sentence into numbers? It starts with tokenization. Tokenization is simply breaking text into units the model can handle, called tokens. The naive approach is to split on whole words, but that has a nasty problem. The vocabulary explodes and the model chokes on any word it never saw in training. So modern systems use subword tokenization. Common words stay whole, but rarer words get broken into meaningful pieces. So tokenization might become token plusization. This is the sweet spot, a manageable vocabulary size, and the ability to represent absolutely any word, even one it's never seen, by assembling it from familiar pieces. It even handles typos and new slang gracefully. So the first step of every NLP pipeline is this. Take the raw string and chop it into a sequence of subword tokens. That's the raw material everything else works on. Tokens still aren't meaning. A token ID is just a label, a lookup number. The leap to actual understanding happens with embeddings, and this is one of the most beautiful ideas in AI. A token ID like 5561 means nothing on its own, it's just an index. An embedding replaces that ID with a dense vector. A list of numbers, maybe 300 or a few thousand of them, and each number captures some learned facet of the word's meaning. Here's why that's powerful. In this vector space, words with similar meanings end up physically close together. King and queen sit near each other. Invoice and payment cluster far away in a different neighborhood. Distance and direction encode real relationships. The famous example is that king minus man plus king plus woman lands near queen, and these vectors aren't hand assigned. They emerge during training so that words used in similar ways drift into similar positions. This is the key unlock. Once meaning is geometry, a model that has seen plenty about cats can generalize to kittens for free because they sit right next to each other. The same idea powers search, recommendations, and in Module 8, retrieval-augmented generation. Embeddings give each word a fixed meaning, but meaning depends on context, and often a word's sense hinges on another word elsewhere in the sentence. The mechanism that handles this is attention. Attention lets the model, when processing a given word, look at all the other words in the sentence and decide which ones matter the most for understanding this one right now. Instead of squashing the whole sentence into one fixed summary and hoping for the best, it dynamically weights the context. Take the sentence on the screen. The animal did not cross the street because it was too tired. What does it refer to? The animal or the street? When the model processes it, it scores how relevant every other word is, and as the shading shows, it puts the most weight on animal, correctly linking it back 6 words. Three things to notice. Every word looks at every other. The relevant words get more weight. So the model builds a context-aware representation, not a fixed dictionary meaning. And the link is made in one step, with no sequential bottleneck and no fading memory. This ability to let context reshape meaning, reaching across a whole sentence at once, is the idea that more than any other made modern language models so good at long and complex text. And in the next slide, we'll see the precise mechanism behind it. Let's make the attention concrete with the actual mechanism. Query, key, and value. Don't worry, the intuition is friendlier than the names. Think of it like a search. For each word, the model creates three vectors. The query is what this word is looking for. I am the word bank. What context do I need? The key is what each other word offers, a little advertisement of what it's about. And the value is actual information each word will contribute. The model compares this word's query against every other word's key to get a set of attention scores. How relevant each other word is. It turns those scores into weights that sum to 1, and then it blends the values according to those weights. The result is a new context aware representation of the word, one that has pulled in exactly the information it needed from the rest of the sentence. That's self attention. Every word queries every other and updates itself based on what's relevant. Do it in a parallel for all words at once, and you have the core operation of the transformer, which you'll run yourself in the next demo. Let's turn tokenization, embeddings, and attention from words into numbers you can see. I'll run it, you watch it. This code tokenizes a short sentence, looks up small embeddings for each tokens, and measures how similar their meanings are, and then runs one self-attention step all in plain NumPy. So let me run this. Those similarity numbers are the meaning as geometry we just talked about. Related words score high, unrelated words score low, and this grid is one self-attention step. Each row is a word deciding how much to pull from every other word. Pause here, change one of the words embeddings in the file, rerun it and watch the similarity scores and the attention grid shift. That's the mechanism, not a black box. We have all the pieces, embeddings and attention. Now the architecture that assembled them and changed everything, the transformer. Before transformers, language models read text strictly one word at a time, carrying a single running memory, and by the end of a long paragraph, the beginning had faded like a game of telephone. In 2017, a paper with a bold title, Attention is All You Need, threw out that sequential bottleneck. The insight: if attention lets every word look directly at every other word, you don't need to crawl through the sentence in order at all. You can process the whole thing in parallel. Follow the timeline. 2017, the transformer is introduced. 2018, BERT and GPT arrive. Pre-train on huge text, then fine-tune and the benchmarks tumble. 2020 and beyond, scaling laws. Bigger models plus more data produce surprising emergent abilities. The GPT-3 era. And today, foundation models power chat, code, and assistant across every industry. One architectural idea, self-attention at scale, underpins the entire modern AI boom we are living through. Let's look inside one transformer block because a full model is really just this same block repeated many times. Data enters as token embeddings, and because attention itself has no built-in sense of order, we first add positional encoding, a signal that tells the model where each word sits in that sequence. So, dog bites man and man bites dog don't look identical. Then comes the heart, a self attention layer where every token exchanges context with every other token, exactly as we just saw. And critically, it uses multi head attention, several attention operations running in parallel, each free to focus on a different kind of relationship. One head might track grammar, another might track which pronoun refers to which name, another the topic. After attention, a small feed-forward network refines each token's representation, and wrapped around both are residual connections and normalization, which are the plumbing that keeps a very deep stack of these blocks stable enough to train. Stack a few dozen of these blocks, and you have a modern language model. That's the architecture, repetition of one clean, powerful idea. Not all transformers are wired the same way. There are three families, and knowing which is which helps you pick the right model for a job. Encoder only models. BERT is the classic. Read the entire input at once in both directions to build a deep understanding of it. They're brilliant for understanding tasks, classification, extraction, search. They read, they don't write. Decoder only models. The GPT family. Generate text one token at a time, each new token conditioned on everything before it. They are the writers. Chat, completion, code generation, and today's big general purpose LLMs. And encoder decoder models like T5 do both. They read an input fully, then generate a transformed output, which is a natural fit for translation and summarization. The practical takeaway, if your task is fundamentally about understanding a piece of text, an encoder style model may be leaner and better. If it's about generating text, you want a decoder style model. Most of what you'll reach for today is the decoder style LLM, but knowing the families keeps you from using a sledgehammer where a scalpel would do. Now, the practical part. And here's the good news, you almost never build any of this yourself. You start from Hugging Face, and it makes running a state of the art model astonishingly easy. Hugging Face is the ecosystem the whole industry standardized on, a hub of hundreds of thousands of pre trained models, plus the tokenizers, datasets, and tools to use them. And the fastest way in is this pipeline API, genuinely inference in about one line of code. You write pipeline, name the task, sentiment analysis, summarization, question answering, and it downloads a suitable pre-trained model, wires up the tokenizer, and hands you a function you can call on your text. That's it. In 3 lines, you have a working sentiment classifier or summarizer before you have committed to anything heavier. For an FDE, this is gold. You can stand up a working baseline for a client in minutes, prove the concept, and only then decide whether you need something more custom or not. Start with the pipeline, earn your way through the complexity. When the one line pipeline isn't quite good enough for a client specific data, Hugging Face gives you the next step up, fine tuning, with a clean, repeatable workflow. The pattern is consistent every time. 1. Load a dataset. Your labeled examples, often via the dataset library, which handles the messy part. 2. Load a pre-trained model and its matching tokenizer from the hub. 3. Tokenize your data so it's in the shape of the model expects. 4. Train, usually with the trainer utility, which wraps the whole loop of forward pass, loss, backprop, and optimization we learned earlier. So you configure it rather than code it. And 5. Evaluate on held out data. And if it's good, save and deploy it. Notice this is transfer learning made turnkey. You're not training from scratch, you're adopting pre-trained model with your data using tools that handle the plumbing. And notice it echoes module 5's life cycle. Prepare the data, train, evaluate, ship. Same discipline applied to language models. Now the everyday deliverables. Three LLM tasks you build for clients again and again. First and the most common is classification. Classification is assigning a label to a piece of text and it's everywhere in business. Routing a support ticket to the right team, billing, bug, or how to, reading the sentiment of a review, tagging an email's intent or a message's urgency or a document's policy category. Traditionally, you train a dedicated classifier on label data, and that's still a great, cheap, reliable option, especially at scale. But modern LLMs can mostly often classify well with just a clear prompt and a few examples. No training pipeline at all, which is perfect for getting started fast or when label data is scarce. The FDE judgment: for a high volume stable set of categories, a small trained classifier is cheaper and more predictable. For a quick start, a fuzzy set of categories or low volume, prompt an LLM. Either way, wrap it with evaluation, measure it against real labels because a classifier you haven't measured is a classifier you can't trust.